Afternoon. My name is Kondwan Muntali from Malawi. I work with the University of Malawi, and I'll be presenting on a transformer, LSTM boost Maize-Yield estimation in smallholder fields of Malawi. I think this is work for one of my students, Matthews, who was not able to come here because of visa issues. So I'll take it up on his behalf. So again, I mean, the logo for 60 there, I think, is just to show that as the University of Malawi, we are still in our infancy, so we're celebrating 65 years of existence. So I'll run you through those. I'm cognizant of the fact that this is an academic stream, so I'll try to be as academic as possible. In terms of background to what we're trying to do here, I think some of you might be aware that for majority of the food production, for example, in Malawi and most of the sub-Saharan African part, is largely produced by smallholder farmers. And when we talk of smallholder farmers, we are talking of people that are producing largely for subsistence, just barely to produce enough for them to eat, but also in very small pieces of land. Usually it's less than a hectare, and we're talking of acres, if it were be. And for us to be able to estimate how much we can produce in a particular year, I think we've largely been using traditional field surveys. And as you might recall, these are a bit labor intensive. But if it were possible that they could be labor intensive but still give us the data in good time, maybe we'd still go with these approaches. But I think they're also delayed in providing us meaningful information for us to utilize to support our decisions. Beyond that, we are also saying that for most of the farming, but also for most of the sub-Saharan part, there are some context-specific challenges that the smallholder farmers face, but also influence what they do as they produce their things. One of the things that is very common is what we call intercropping, where you've got one or two main crops intercropped with several other crops. And therefore, that poses some form of challenge in terms of if you have to use some of these tools like remote sensing and things of that nature, where you've intercropped a lot, you really need to have very good data for you to be able to do that. And data is also not readily available for this particular part. And so it gives us a bit of a challenge in terms of how do we begin to estimate or at least have an idea of how much we can actually produce in a particular year and therefore plan accordingly. However, we do have some of the free available data like Sentinel, and it has been very promising for a good part, especially in the sub-Saharan part. However, the capabilities of this and this utilization in our parts has not really been that much of promising. Now, what we are trying to fill in is to try and use the newer models that are coming out, like convolutional neural networks, transformer models, to try and compare them to the classical approaches that have already been existing and see if they can actually fit in the context of Malawi for us to be able to do these tests. And so for the visual transformer and the LSTMs, they're still untested in most of the sub-Saharan African context. Not that no one has done anything like this, but there's still a lot more ground that we need to cover. But over and above that, we also need to have a spectrum of possible accuracy, complexity comparisons against the computational resources that we need for us to achieve those things. And that can now guide us in terms of how do we deploy some of these tools in this context. And that's where it takes us to what we are now trying to achieve, which is to try and evaluate a set of remote sensing techniques for us to be able to use, to predict yield for maize. And again, maybe just to highlight why we're emphasizing on maize. Maize is a staple food in Malawi and probably even in the region. So, I mean, if it can't produce food, it means the country is hungry. Technically, that's what it means. Specifically, I want to be able to build a dataset for us to be able to do some of these things as a starting point. But we're also infusing climatic data, but we're not throwing away the labor-intensive ground truthing that will require. And like I said, overall, we need a spectrum of possible models that we can use that are tailored to the sub-Saharan context, particularly Malawi. But we're not moving away from the advanced approaches like deep learning architectures for the visual transformers and also the LSTMs. And over and above that, we now want to see the trade-offs that exist between the complexity of actually building the model and the accuracy of the model versus what we can actually afford in terms of computational resources, and determine now which of these modeling approaches will best balance the predictive power, but also the operational feasibility in the context that we are operating. So the study is in a small town in Malawi, the former capital, Zomba. So we have about 8 plots of rain-fed smallholder maize fields. Like I said, these are very small holder farmers, between 0.9 and 0.2 and 0.9 hectares. We have collected some Sentinel-2 level 2 images between December 2024 and February 2025, and this is deep in the rainy season, and that's the reason why we have highlighted that this is rain-fed production. So we needed imagery within that particular frame. But we're also adding extra data just to support, like I mentioned, climatic, but also data that explains the various soil conditions. And we also use the services of the extension officers from the Ministry of Agriculture to help us in terms of the grain yielding, which they use the normal approaches like I've mentioned, that they actually go and visit and sample some of the locations. And so we are using 10 by 10 meter quadrants per field, and then you dry that to around 13% of moisture, and then you convert that to kilograms per hectare. So you can now have an estimation of the production within that 10 meter by 10 meter, and then you interpolate that to cover the whole field. And we're using that as a measure to compare with what the models will actually be able to predict against what is actually the standard practice on the ground by the ministry. So our methodology, an overview, we did some cloud masking for the satellite imageries, and then we rolled them over 10-day medians. We also did some reprojection and upsampling to 1 meters, and this is largely just for the imagery to be compatible with the advanced recurrent architectures. We also computed some spectral indices, NDVI, EVI, red edge, and also NDWI as part of the data that we need to include here as a feature stack to help us with the the modeling. We also tiled each of these into 32 by 32 pixel sliding windows to generate the learning patches for the models. And we patched all these into quadrant level reference yields that now informed the training of the model and eventually the evaluation. So this just gives us the workflow in terms of what exactly happened. And as a workflow, we have the various inputs, primarily the satellite imagery and also the field-based data, plus the ancillary data in terms of climate and soil data that we obtained. I think we didn't use much of the rainfall, we just used the temperature and the soil data. And the modeling happened in between. The evaluation metrics, so the models that we have tried to compare are the linear regression, the XGBoost, and then the convoluted neural network LSTM, plus the frozen visual transformer, and then the boosted visual transformer LSTM, and see how these compare against each other. And the metrics that we've used is RMSE, and then the cross-validation, we're using the LOFO approach. And the other key metric was on latency and throughput, because it's important that we understand how we can actually, if you have to scale this nationally or regionally, it will be important that we're able to get the results in a specific time that will inform some of the decisions. So we'll resort to that in the discussion. So having run and implemented the models, this is how they are fared, and it's quite obvious from the results that the recurrent models like CNN, LSTM, and the boosted visual transformer LSTM have actually outperformed the non-recurrent baseline, like the classical machine learning models like linear regression, XGBoost, and the others. And this is quite significant statistically. And from our assessment, the visual transformer LSTM boosted yields an extra 0.092 tons per hectare gain in terms of in terms of mean error over the second best, which is the convoluted neural network LSTM, and it's also significant statistically. And for most of the baseline models, there is no significant difference. So they have been outperformed as a block, but also within them, there isn't much significance in terms of how I think you can see the RMSE for LR, XGBoost, and frozen. They're all around 0.21, 0.28, 0.22, thereabout, which is hugely different from the other last two, which are 0.08, but overly different from the last one, which we are saying is the best, the visual transformer boosted LSTM, around 0.02. So the implication is that if you just take this, then the visual transformer boosted LSTM is the most accurate. But for us, this is not enough, because we now need to take the next step and discuss how exactly this is being affected in terms of latency. How quickly can we get the results if you have to take this nationally? So while the visual transformer LSTM is the most accurate, when you look at the accuracy versus efficiency trade-off, it's not the best, because it's 4 times lagging from the CNN LSTM model. So we feel that the CNN LSTM is the best in terms of operationalizing the modeling, because it's giving us a near optimal accuracy while delivering the predictions in a roughly 9 milliseconds per patch. And if you have to extrapolate that to the national grid, then it's basically well suited, because it would take us around 7 days for us to be able to run through the whole country, and given the resources that, the type of resources that we've been using to run this. And if it's anything that we need to use, for example, national dashboards and things of that nature, I think a 7-day lag is not very bad for us, as long as we can actually get the imagery. So we also did some testing to check in terms of how it can actually perform when we improve the computational resource, just to see whether it's going to be worth it. I think a small improvement in terms of the processing is actually reducing it from 7 days to just a matter of hours to process some of these things. So it's really working very well. So in a nutshell, I think that's basically what we have done. And in terms of contributions, we feel, I think, this will give us a benchmark for us to be able to estimate the yield of maize in Malawi. And while the visually transformed boost-LSTM is a good benchmark, we'll still go to the CNN-LSTM because it's operationally feasible within our context. But it's also a beginning in terms of building data, a data set that we can now use as we go to be able to inform the various models that come in, both in terms of imagery, the yield data set, but also just the models that are able to do this. Over and above that, we are of the view that I think this can give us a good chat guide to inform the deployment of some of these models even beyond Malawi. But also, I think it gives us a reproducible leave one outfield protocol for data scarce regions like Malawi and a good part of the most of sub-Saharan Africa. So thank you very much for your attention. I think I can now leave it for questions. Thank you. Oh, yeah, okay. Yeah.
How do the compute resource requirements compare between a neural network and a MIST transformer?
Okay. I think we. Yeah. Yes, that's what it would mean. We need a lot more GPU for it if you have to use. But I think our emphasis was not in terms of comparing the amount of resources we need, but given the resources that we have, which one will be the best model available. So if you're improving the resources, we improve across all the models and see how they are faring. Actually, that's what we did when I was saying that I think if you improve the processing for the next level, I think for the type of machines that we are using for this, I think we're taking 7 days for the CNN boost-LSTM. But if you just notch it up, I think it was reducing to about 7 hours. So, yeah. Yes.
Can you please, can you explain your local cross-validation? Is it 1 hour? Or
Yes.
Okay, so you didn't try, I'm wondering whether some sort of spatially informed cross-validation would be meaningful here, because
Yeah.
that could happen in the variation space, and you might actually spread all these.
Yeah, I think you're making a lot of sense. I think we didn't think about that. I think we can try that in our next iteration. I think it would work. Yeah. Yeah, because I mean, I think this is random leaving out some portions. I think we need to be targeted. Yeah. I think. Yeah. Yeah, I think it would help to be targeted in terms of how, spatially, yeah, it would make sense, yeah.
Can you explain how you have expressed time in your LSTM? Is it absolute or relative time within the year, or is it time until harvest, let's say, or how do you express it? Because I'm wondering.
I think this.
I'm thinking about the efficiency because you're retraining stuff every day.
Yeah.
So that if there is a way to relativize it, there's some information
I think this is within the growing period until the harvest. So it's not for the whole year.
So you're encoding a date or encoding negative time, let's say, from when you're saying like minus month, minus.
Yeah.
Month,
Yeah, the latter.
the later.
Yeah. Yeah. All right. Any questions? I think I can hand over to you, Chair. I think I'm not seeing any other hands. Thank you.